And learning goals today says, I can evaluate and simplify expressions containing rational exponents. So we just worked with integer exponents. What's the definition for an integer again? A number on the number line. Well, not all numbers on the number line are integers. So we just worked whole numbers.
Real.
Whole numbers and their
Opposites.
So we know we just worked with positive exponents in integers. We just worked with zero exponents. We just worked with negative integer exponents. So we have been working with integer exponents in lesson 6.1. Now we're moving into rational exponents. Well, what does rational say to you? Real? Yeah, they're going to be real. Rational. The word ratio is in it. Does that help? Rational. What's fraction? A fraction, yeah. So we're going to be working now with fraction exponents. So we're going to be taking something to a fractional power. And that fraction power, that rational exponent, may be less than 1 or it may be greater than 1. We got to know how to handle both ways. Okay? So right here, would you circle these two? If we have it written like this and we have it written like this, they really mean the same thing. And here's how you actually say. The first one is said the nth root of b. The other one says b to the 1/n power. They actually mean the same thing. Here's what both of them are really asking you. What number times itself, n number of times, gives you that b? What number, n times itself, so n factors of that, when you multiply that many n's, you should end up with b. We call n the index. It's kind of an important mathematical term you understand. N is the index. Another way to talk about the index is they often say, call it the root. It's looking for the root of b, and that's what we're going to need to find. We're going to need to find what is the root of b. Okay, so n is the index, and he's saying, okay, help me get the root of b. So let's just start practicing here. If we have 8 to the 1/3 power, that's really asking us, because another way to write that would be like this. You could do this over in the margin. Another way to write this would be the 3rd root of 8. So 8 to the 1/3 power, the 3rd root of 8, is just asking us for that 3rd root of 8. It's asking for what number times itself 3 times gives you 8. And what number is that?
2.
2. 2 times 2 times 2 produces 8. Therefore, we can say 8 to the 1/3 power is 2. So for those of you who've been, kind of confusing the exponent as a multiplication sometimes, like maybe if it's 4 to the 2nd power, you have taken accidentally maybe, your brain just says 4 times 2 is 8, 4 to the 2nd power is 8. Is that what we do? No. That is saying what? 4 times 4 times itself, and we get 16, not 8. Same thing here. We are not saying what is 8 to the 1/3 power. Do we multiply and take 8 times 1/3 and get 8/3? That's not what this is saying either. This is saying instead, what number times itself 3 times will give you 8? Well then, what's 81 to the 1/4 power asking us for? Which root? The 4th root. It's asking us for the 4th root of 81. So in other words, our n is what? What's our n? 4. And our b is? 81. So again, another way this can be written is the 4th root of 81. So we have to find what number times itself how many times? 4 gives us 81. So it's basically you're going to show it like this. I need 4 of the same factor that in the end, the result would be 81. Think you got it?
Yeah.
What is it?
3.
3. Okay, because I've been telling you to memorize some of these powers, haven't I? 3 times 3 times 3 times 3, or in other words, 3 to the 4th power is 81, isn't it?
Yeah.
So we would say then that 81 to the 1/4 power is what? 3. That's our answer. Questions? No? Okay. Well, in this next one, it's 121 to the 1/2 power plus 256 to the 1/4 power. And then I wrote them as roots. Why don't I have, do you see an index here anywhere? No, this is one of those invisible things. What would the index be there? When it's not showing, what do you need to know it is? 121 to the 1/2 power, it's actually 2. So when there is no index written there, that's the only root that we don't put the index there, because that's understood that if there's not an index written there, it is the second root, the square root of that particular number. So when it is empty, it's got what again?
2.
It's really a 2. So we are really looking for the square root of 121, and we're going to add to that the 4th root of 256. So let's show some work here. What times what equals 121? And what times what times what times what equals 256? And by the way, that what always has to be the same thing in each of them. So what's the what in 121? 11. The square root of 121 is 11. So we can replace that with 11. And what's the what in getting 256? You think it's 4?
Yeah.
Okay, let's give it a quick try here. 4 times 4 is
16.
16. 16 times 4 is
64.
64. And 64 times 4 is, you're pretty convinced of that? Yeah? Okay. So then we're going to say that the 4th root of 256 is 4. And 11 plus 4 is 15. So again, all I see on your papers tomorrow, a problem like this is 11 plus 4 equals 15. Do you think I'm going to trust that you didn't use the calculator? No, I'm just not going to be able to. I'm sorry. And again, when you take this quiz coming in a few days, you're not going to be able to either. So, don't let your calculator do the thinking for you. Okay, 27 to the 1/3 power, subtract 1 to the 1/5 power. What root are we looking for of 27? The 3rd root. What root are we looking for of 1? The 5th. So we're looking for what multiplied by itself. 3 factors of it will give us 27. What's that, AJ? 3. Okay. 3 times 3 is 9, times 3 again is 27, so I can go with 3 for the 3rd root of 27, or 27 to the 1/3 power is 3. What does the 5th root of 1 mean? It's 1? Do you think we need to show work for that one?
No.
Convince me why not.
Because it's just 1
Well,
times
because-
5 times, and it's just going to stay 1.
1 times itself 5 times. What if it was 10 times?
Still
It'd still be 1. What if it was 2 times?
So it's 1 till
So in other words, no matter what root you're looking for of 1, it's always going to be 1. Well then, let's not work so hard. Okay, so that's 1. So we're going to subtract 1. And 3 take away 1 is
2.
2. Okay, I want you to observe something about every problem that we did in this one. The rational exponent, what did they all have in common? They were all whole numbers?
They weren't above 1, they were from 0 to 1.
They were less than 1. They were between 0 and 1. In other words, they all had a numerator of 1. Okay. In this particular case, they all had a numerator of 1. That's probably even more important than the fact that they're between 0 and 1. If they have a numerator of 1, we can do what we just did. Figure out what number times itself, the denominator times will give you that base. When the numerator is 1, that's all we have to do. Take that denominator and say, oh, you're the root. And now since you're the root, that means I need to find the number that multiplied by itself this many times will give me that base. So let's go to the back side now. When the fraction exponent has a numerator that is a whole number greater than 1, notice I'm talking about the numerator, not the rational exponent. But if the numerator of the rational exponent is greater than 1, then we're going to have to do some kind of like creative thinking. If I have b, base b, raised to the m over n power, I can rename that as a power to a power. In other words, I can unsimplify it. Because remember, what do we do when we take a power to a power? What do we do with the exponents? What do we do with those exponents? Power to a power. We multiply. So when we're unsimplifying, we have to think about what was the multiplication problem that this product came from. So what did m over n come from?
1 over n times m over 1.
Yeah, 1 over n times to the nth power. So we have actually, this is really, if I took 1 or b to the 1 over n times m power, well, m is not a fraction, so I'll make it into 1. What's 1 times m upstairs? M. What's n times 1 downstairs? So this takes us right back to b over m to the n power, doesn't it? So when we rename it as a power to a power, now we can break it apart and say, what's this really asking me for? So what root do you think that is asking for, and raised to what power? Considering in the front side, we just did the ones with numerators of 1. So what root is this asking for, first of all? What root of b is it asking for? The nth root, yeah. That denominator, the denominator is asking for that root of your base, and then we're supposed to raise that answer to the what power? To the m power. To the nth power. Okay, well then we're going to have to break these into kind of like a 2-step process. So we have 16 to the 3/4 power. I've already renamed it as a power to a power. Notice, what it is as simple as doing. What do you really end up doing?
Just taking the denominator and then putting a 1 above it.
Okay, so you're replacing the numerator with a 1,
And then putting what the numerator was outside.
and then the numerator becomes outside the parentheses, doesn't it? Yeah. Because again, whatever you rename it as, if you multiply that back, it better take you back to what you started with. Would 1/4 times 3 take us back to 3/4? Yes? Okay. Well then what's this really asking us for? It's asking us for what? Okay, because what's it asking for first? How'd you get to us? Asking for the 4th root of 16. That's what it's first asking for. Saying, what is the 4th root of 16? And then it says, after you get that, will you cube that? Will you take it to the 3rd power? So we need what times itself? 4 times gives us 16.
2.
That's 2, isn't it? Okay. 2 times 2 times 2 times 2. So we end up with our parentheses become 2. the fourth root of 16 is 2. Well, are the parentheses even important anymore? No, because it's not negative. So what's 2 to the third power? 8. So 16 to the 3/4 power is 8. Questions? Okay, I want you to try rewriting number 6, the 25 to the 3/4 power. I just want you to start by writing it as a power to a power for me. What would that look like as a power to a power? Okay, who would like to share their wisdom with us?
25 and a half.
25 and a half?
No, 25 to the
25 and a
One
third.
half.
Oh, 25 to the 1/2 power
Yep.
in parentheses.
And then 3 on the house.
raised to the third power. Make sure those look like the exponents, okay? So 25 is being raised to the 1/2 power, and then that is being taken to the third power. So it's really asking us for the square root of 25. Is that what it's asking for? Is that what 25 to the 1/2 power means?
Yeah.
Remember, that's the invisible index. And then after you get that, it's saying take that and cube it, or take it to the third power. So, you know what, we're not going to show word for this one. What is the square root of 25? 5. And 5 to the third power,
125.
125. Okay, we're going to do one more, and then I'm going to ask you to do some critical thinking for me. Would you do number 7 totally on your own? Figure that one out. Number 20, or number 7, 27 to the 4/3 power. When you're done, will you check me out, please? I know what I'm doing. Do I know what I'm doing?
Yes.
I got this?
Uh-huh.
You got this?
Mhm.
Okay, cool. Okay, now, let's do some critical thinking. Notice the fraction exponent in those 3 problems that we've worked so far back here. And then I want you to compare the base to what we got when we raised it to that fraction power. So, no, just, pay attention to, first of all, what, make some comparisons there. And then make a comparison to this, the base, compared to what happened here. The base raised to that fraction compared to that. The base raised to that fraction compared to that. Any conclusion you think you can make so that when you're done working these problems, especially on an assessment, when you get graded on it, you could be, and no calculator, I have stored them all up on my desk and I'm going to put them on eBay and sell them all. But yet, you want to make sure you got it right. And all the begging in the world doesn't get you your calculator back. So, it's always good in math to be able to say, well, at least, is my answer reasonable at least? Even if it's not, at this point you're not sure if it's right. You might be pretty convinced, but you at least should be able to say, is it reasonable? So come up with something that could help give you some reasonable thinking here.
If it's a fraction that's bigger than 1, it's going to be bigger than what it started because it's 3/2 and 25 ends up on 25.
Okay, so 3/2 is greater than 1. 4/3 is greater than 1. And in both of those cases, the results were greater than the base, weren't they? Okay? Well, then the reverse, I mean, kind of like the undoing it, that's kind of like saying that if the fraction is between 0 and 1, it's less than 1, between 0 and 1, then the result we get should be smaller than the base. Would that be a good thing to test and say, you know what, I had a fraction greater than 1, how did I end up with an answer less than my base? Something has to be wrong, right? Okay, so keep, you know, if you need to make a little note about that, or you're going to remember it, whatever, but that would be a good way to test to see if you at least have a reasonable answer. Good job coming up with that, Austin. And anybody else who might have had it but just was not sharing. Okay, 1 to the 4/5 power. What does that mean? 1 to the 1/5 power raised to the 4th power. Well, the 5th root of 1 is 1. We said any root of 1 is 1. And 1 to the 4th power now is still 1. Well, how do you feel about what if that had been 5/4? Would that have changed it? Does this even follow our rule that says if you have a fraction between 0 and 1, you should get an answer less than the base? Does this follow that rule?
Anything
It'll be the
times 1
same.
is just going to be 1.
Yeah, because there's 1 has its own special rule, right? 1 raised to any power is going to be any power. Whether it's an integer or it's a fraction, are you convinced that even a negative power, would 1 to a negative power also be 1? What if I had 1 to the -3 power? How would I rewrite that as a positive?
1 over 1 to the 3rd.
1 over 1 to the 3rd.
But it's still gonna be
Just
just
still
1
one.
because 1 to the 3rd.
1 to the 3rd is still 1, and 1 divided by 1 is still 1. And what's 1 to the 0 power?
1.
1. And so it looks to me like no matter what power we take 1 to, the answer is always going to be 1. So we can just write 1, can't we? Okay, how about 0? This is saying 0 to the what power? 1/6 power raised to the 5th power. What times itself 6 times gives you 0?
0.
0. Okay. 0 times itself 5 times gives you 0. Do you think 0 has its own special rule?
Yeah.
Okay, then state it for me.
No matter what you multiply it by, it's still going to be 0.
Well, that's a multiplication rule for
Yeah.
multiplying by 0. We're talking about powers.
Whatever power you do, it's still going to be 0.
Okay, do you guys all agree with Austin? He says no matter what power you take 0 to, you will always get 0.
Yeah.
AJ?
Isn't it the same rule for 1?
Yeah.
That's a 0.
But now, so 1 to any power is 1. We've already tested that and said that's okay.
What if
But
it's
now
zero?
we're testing to see if 0
It's
is
zero.
wrong.
0
Why did
times
0 to the 0 power be 1 then? Because anything to the 0 power is 1.
Really? You think so?
Well, that's what.
I thought we learned
Wait,
a
no, it
property.
was anything but 0.
I thought we learned a property about taking something to the 0 power. What was the only thing the base could not be?
Zero.
It could be 0. Oh. So 0 could be raised to any power except 0 then? Technically, okay.
well, yeah.
It would still be 0.
Huh. How about a -3? How about 0 to the -3 power? What would that be?
1 over
The
0.
calculator.
Try it with your calculator. What's 0 to the -3 power?
Just show
So
as
it's
error.
0.
Does it show up as error?
Please.
Domain error? That means whatever you put in there for x, it doesn't like it, does it? Oh, why doesn't it like
You
it?
can't multiply 0 by 0.
You can multiply 0 by 0, you get 0.
Yeah.
Yeah.
can't divide it.
We can't what?
Divide it
By 0.
Oh, and what would 0 to the negative 3 power be written as a positive exponent?
1 over 0 to the third.
1 over 0 to the third, and 0 to the third is
0.
0, so we have 1 divided by 0. Can we divide by 0?
No.
No. Okay, so we have got to refine this rule even some more. It can't be raised to the 0 power, it can't be raised to a negative power. So what can we say? 0 raised to
Positive.
a positive power,
Other than.
all, well, no,
Oh,
0 is a
0.
positive or negative.
Positive.
0 raised to a positive power will always be
0.
0. Oh, hallelujah, we got it. Okay. 4 to the 2.5 power.
Wow.
Holy moly, what are we gonna do this
Ooh,
for?
can you?
Turn it into an improper fraction.
Unsimplified, what do you mean, Kat?
Yeah, I.
Give her a chance.
Turn it into
Yeah.
Oh,
No, he
stop
said it.
talking for
No,
it.
he
Tell
said
me what you want
Turn
to
it
say.
into an improper fraction.
Thank you very much. What improper fraction would 2.5 be?
5.
5 seconds. Okay, 5 over 2. That would be your first move. Rename the mixed number as an improper fraction and then take it from there. So now we are looking for, which root of 4?
Square root.
The square root, because it's 4 to the 1/2 power, so we're looking for the square root of 4. And then what are we going to do with that? What are we going to do with that square root of 4? Take it to what
Take it to
power?
the 5th power.
Take it to the 5th power. So we have this. This is really what we have, don't we? Either way, it describes what's going on. Either way. And the square root of 4 is 2. And 2 raised to the 5th power is 32. Everybody convinced that AJ knows what he's talking about?
Most of them.
Yeah? Okay. 2 times 2 times 2 times 2 times 2 is 32. Okay, I agree. Open your books to page 399, please. Very bottom of the page, we're going to do check it out problem number 3. But to do check it out problem number 3, we're going to need to read what was happening in example 3. So would you read the bold print in example 3? All of you to yourself, because otherwise somebody will read and you'll stare out into space. Okay, well they found the number of calories that a 16-kilogram dog needs each day. We're supposed to, in number 3, find the number of calories that an 81-kilogram panda needs each day. So where should we start?
Using the equation they gave you.
Okay, using the equation they gave us. So we're going to say C equals 72 m raised to the 3/4 power. Well, it would be good if we knew what capital C stands for and what little m stands for. What's
C is the calories.
Calories.
Oh, isn't that clever? C
M is
for
the
calories,
weight.
and little m is the mass, or in other words, the weight, right? Okay, so what are we going to, we're going to substitute what in for m then?
81.
81. So I'm going to insert a multiplication dot there because 72 next to m to the 3/4 power really means multiplication. Do I take the 72 times the 81 first?
No.
No.
Or do I do that power first?
Do power.
Yeah, we do the power first. So we're going to not, we're not going to ditch these other guys. They're going to keep coming along, but we're really going to say this really is the 81 to the 1/4 power, or the 4th root of 81 if you'd rather write it like that, raised to the 3rd power. So the first thing we need to look for is what times itself 4 times gives us 81. What is it, 3? Okay. So now we can replace 81 to the 1/4 power with 3. And what would we do next?
Take 3.
3 to the 3rd power.
3 to the 3rd power has to be next. Power before multiplication. So what is 3 to the 3rd power?
27.
27. Oh, no, you don't get to use your calculators, get busy, start doing some multiplication. You already got this, AJ? Okay. Did you check your work, because we're counting on you to be ready. Okay, you got it? What is it?
1,944 calories.
You got it. $1,944 calories that panda bear gets to have. Okay, so making sure that we know also how to evaluate when we substitute following order of operations, following what we just learned about rational exponents and so on. Okay? Questions, anyone? Okay, Ben, why don't you get out your loose leaf if you have not yet put a heading on it?